Hello everyone, so today we are going to do Leetcode daily challenge. Triangle. That is the question which we are going to do. So in this question, we are given with 2D vectors, and in this 2D vector, we are required to find the minimum sum, and we need to return that sum. So the thing would be something like this, that in this triangle which is being given to us, because it is mentioned that given a triangle array. So as they have given us this triangle array, so that simply means that one element is there, then 2, then 3, then 4, and then 5, then 6, then 7. Means that each step one element would be increased. So that's how it becomes a triangle. And then we are required to return minimum path sum from top to bottom. So we need to include this, and either of this would be there, either of these would be there, either of these would be there, who would include to minimum sum. So this is how this question is going to be. So for each step, you may move to an adjacent number of row below. More formally, if you are at index I on the current row, you may move to either index I or index I plus 1 on the next row. So they want to say that 2, 3, I'm not click this, if you say like this, 3, 4, and then 6, 5, and 7. So if we take this 4, so it can go here at 5 also, or it can go here at 6 also. Do it like this. Means if we here, then it has access to both of the numbers which are there. Basically here 6, and here it will be 5, and here it will be 7. So when it is at 4, the 4 could have access to 5 also and 7 also. When we are at 3, the 3 could have access to 6 also and 5 also. So this is the thing it wants to say to us. And like this only, this particular question is somehow aligned with the part sum question, part sum 2 question, where we were given with a tree, and we were required to find the minimum path sum. So like that only, this particular question is also somehow similar to that. But it is not a binary tree here, because 3 is also pointing to 5 and 4 is also pointing to 5. But in binary trees, such case is not there. So somehow modification is required to be done in that scenario. So let us check about the time constraints which are given to us. The time constraint is that the triangle length, that is the number of rows, would be maximum 200. So maximum 200, if we go ahead with n square solution, it would work fine. And each time the first row which is there, its length would be 1 only, and each time the triangle of I dot length equals to plus 1. That is, when it is 1, then it would be 2, then it would be 3. Means the length would increase at each step. This is the thing which they are saying. And next, the elements which are there, they could go till max 10 raised to power 4 or minus 10 raised to power 4. This is the thing which they have given to us here. So these were the constraints here. Now I have created the explanation for the same question. Let me show you that. So now the thing is that we are given with this particular array, not the array but vector of vector we are given with. So what we are required to do here is that we can create a tree like this, right? Just for explanation purpose, I am creating the tree, and it is not just complete tree. It is because we are having these two pointing towards same number. Now, the first approach which comes to mind is the greedy approach, because we are required that this is 2, then we'll check which one is smaller. 3 is smaller, then we will put this and go ahead with this, then we'll check which is smaller. 5 is smaller, then we will go ahead with this, then we will check that which is smaller, 1 or 8, and 1, so we'll go with this one. So this is the minimum path sum which we can find out. This is alright with this particular, but there could be some other case also. The case something like this, that we are means at the starting only, say here it is 4, but if by chance it was 0 and this was also 0, means not this one. So this was, then this would have been the path with minimum sum, right? So in that case, greedy approach won't work here, because greedy approach is somehow finding the local minimum for a global minimum. But here that won't work. We are required to find out overall minimum in this particular question. So that's why this won't work. So in all that context, now comes the part that we can't use greedy approach here. Then comes the part that we can use DFS. But in DFS also, how we would be using DFS here? Because it is vector of vector, it is not a tree, right? So in that context, we can directly go to the base at what exactly a DFS is like. DFS is also of two types, either recursive or iterative, right? So if we think in terms of recursive approach, then how the things would be. So we are required to think a solution in that direction. So I've written here that we can work on the possible path. Okay, my cursor was not visible. Possible paths from root, thus it is somehow becomes a question similar to path sum 2. But this is not showing exact behavior as binary tree, so we need to modify our approach. This is thing which I was saying earlier. So now let us go ahead with the recursive approach. So the recursive approach is somehow like this. A 2 is given to us, and 3, and then 4, and so on. So we'll go ahead with one path, that is 3, then 6, then 4. Now it hits the base case, that is the leaf node. Here there is no leaf node. Here it would be something like that. It has hit the end of the vector of vector. So now it will move towards the parent caller after collecting the minimum sum here, because it is the leaf node. So its left and right both sides would be 0 only. So here the minimum it will be getting the number itself, that is 4. Then it will return this to its parent caller, which is 6. And at this moment of time, here we will be having the 4 plus 6, but it also have its other side also, right? So it will go ahead with that one also. Basically, our recurrence relation here would be something like that at a particular node, we would be checking for two cases. And those two cases are that if we are at ij, then we need to add I plus 1 j, not add, but we need to find minimum of I plus j, and we need to find I plus 1 j. This is the thing we are required to do, means basically find the minimum out of both. So this is what we would be doing here. Now comes the part like this, only we would be doing for this whole tree. So here we got for 6, 4 and 1. This was there. So 1 was the minimum. And then we are also required, means at a particular ij position, we would be doing this. Plus we will be adding the triangle of I and j, means that particular number itself. We are required to add that also and return that to its parent caller, which is 3 here. So 1 plus 6, basically 1 was the minimum, so 1 plus 6 would be returned from this side. And now this 3 would simply check the 5, and then 5 need to go ahead again. So it will check for the 1, and like this only, it will now 1 has minimum sum of 1 only. So now 1 will return to 5 as 1 only. and 5 will check for 8, and then 8 will return 8. Then out of 1 and 5, 1 is the minimum. So 1 will add up to 5, and then 1 plus 5 would be returned to 3. So now out of both sides, so 1 plus 5 is the minimum, right? So 6 plus 3 would be returned 2 or 2. So like this only we got 7 plus 3 from the left side, and like this we'll calculate for the right side. So at the end we'll get 9 and 10, right? After adding 2 to minimum of this, which would be 9. So we'll add 2 to it, and now our answer would be 11. So this is the minimum path sum which we can find in this particular triangle which is being made. So this is how a recursive solution would be. Here we are able to go ahead because of this particular thing only, means this particular recurrence relation. So basically a recurrence relation which is here is something like this, that for a particular function, we say that for a particular state, how the things would be, that our function would be something, means our answer would be something like this. That function, in that we will be passing this ij, and then we would be having this I plus 1 comma j, and we would be figuring out minimum out of both. Minimum out of both of these would be there, plus we would be adding the present input which is there, and in that I and j. So this would be our recurrence relation which we are required for going ahead for finding our possible solution. So this is a thing which is required here. Okay. So this was about recursive solution, but as we can see that this recursive solution would be surely having time complexity as exponential, because we are going ahead with the choices, right? So our time complexity would be something like this, 2 raised to power, and it would be something n into n. This would be a time complexity, and the space complexity would be the height of this particular stack. Means each time stack would be having that much element only. So the space complexity would be order of the number of rows only, that is n. So the thing would be, the solution would be something like this. So this much time complexity is not permissible, because if it would be like something like this, so it won't work out. So we need to memoize this particular solution. How memoization would take place? It would be something like this, that as per the constraint, we are required to memoize the repeating subcases. Here there are a lot of subcases which are repeated. So that, and at each point we are required with row and column, because this was the fact. This was row and this was column, right? At each point we are required both of these. So we need a 2D vector to store that particular state. So like this only we would be able to memoize a solution. Now as we were able to memoize a solution, we can also use a bottom approach also. It was a recursive approach, and now we can also use the bottom up approach also. So in that, how would be doing? Our state would be same as the way we were using in memoization. So our state would be TP of row and column, and our transition would take place like this. The recurrence relation which we were having, in that case we can use that case only. Earlier what we were doing was, we were doing I plus 1, j plus 1. But here we would be doing I minus 1 and j minus 1, because it is bottom of TP. And I minus 1 and j. So this is how our transition would take place. But this is the main transition. We also need to take care of some edge cases which were already being handled by recursive and memoise solution, but it is not being handled by this TP solution. So that I'll show you in the code itself. And one more thing is there of the solution. While coding, you'll have a look at that particular case also. So the thing is that we could try to make it in place that is in that input array itself or without using some extra space, or even it could be reduced to order of n phase complexity also because of the behavior which this particular solution is showing. But I'll show you the solution of in place where we would be using the input array itself. So because of behavior of DP solution, we require just one row down to it and not all rows. So that is the main observation of a DP solution. So that's how we can directly convert this particular solution to, rather than using an n square space complexity, we could reduce the space complexity to order of 1 itself. So time complexity of this solution would be n square only, but the space complexity would be order of 1. Here the time complexity would be order of n square, but the space complexity would be order of n square again, and the same would be for memoized also, and this is for bottom-up also. So this is how we came up with brute force approach, that is recursive, and then we optimized the solution to memoization, and then we got a hit with DP, and then at the end we optimize it in context of space also. So now let us go ahead with the coding part. So here are all the solutions which I have written for the case of recursion and memoization. So let me show you this. Okay, so for this particular recursion part, what we are doing is we are directly going with this triangle 0, that is the row, and this particular is the column. We are directly starting from the zeros one only, and here what we are doing is, this is our base case. So for this particular base case, if row equals to triangle dot size, then we are required to return 0. The way we reached 4 there, right, and this was the base case because here it would be having 0 0 only, so it will return here 0, and this will now start returning itself. So in that context only we are returning 0 here. So now we are required to check for the next columns, right? So in that context, what we would be doing, we would be adding our present input which we are given with row and column. Then we will be calling both of the functions the way I had told you there only, row plus 1 column, or row plus 1 and column plus 1. So like this only we are going ahead and calling again and again this recursive function, and this is how our solution would be going ahead. So I don't know why it is showing space like this. Might be because I have increased the size. Don't know. Because I have commented in that manner so that it could be easy to explain. But no issues. I've already explained now. So for memoization, how we are going to go ahead is, again the same base case and the same conditions here also. Here we are just taking a minimum sum with int max, then rows and columns which we are there. Why we are taking both of these? So that we could define the size of this vector of vectors, means extra space which we are using, basically the 2D vector, row, number of rows, and column, and initializing it with -1 because we want to use this particular DP vector of vectors for a solution. So at the end, minimum sum would be equals to the function which we are calling with 0 0 and our vector, and at the end we will be returning this minimum sum. So the thing is, when they both become equal to the size of the triangle, then we are returning 0, same as the base case which was there. And if it is not equals to -1, then in that context we would be returning that particular vector row column as it is. Else, now we are required to basically call that particular recursive function only, but we would be assigning it to our vector side by side at that moment. So this is how we memorize it. Because of memorization, we have added this particular step, and this particular is being added, and yeah, these all steps are also added, and this V is also added because of memorization. So this was all for the memoization. Now comes the part for bottom-up approach. So for bottom-up approach, everything is again the same, the way we were doing in memoization. The only conditions which are changed are these conditions only. And yeah, here we are using in loop format because now it has become iterative and we are starting from 1. Here we are starting from 0 but going till that particular row size because each row is changing. That's it. Now here the thing is that we are taking rows in column is signing the same as it is, but we are initializing the v of 0 0 with triangle 0 0, the root value itself, because at the starting it will be having that only value. Now at the end, not at the end, but the main algorithm is something like that when j is equal to 0, that is the first column is there, and at that particular position we'll check for the previous row but at the same column, and we'll add that particular value to our present block and the present input which is being given to us will add to that. And if it is the last column, then that condition we will add up the previous rows and columns, because the fact is that we are having 1 then 2, right? So see, if we are given 2, 3, 4, basically I'm saying about elements. So when we are required to add these get the minimum at this particular position, then we are required to add this number and this number is basically I minus 1, 0 minus 1, right? So that's why we are adding like this, and this is the mean recurrence relation which we are using from before only. Only changes that I minus 1, j minus 1, I minus 1 and j only, because we are getting our solution in bottom-up manner. So that's why we are doing like this. And at the end, this also changes. Earlier we were returning the recurrence answer from the recurrence relation, or we were returning that minimum sum from that variable, right? But now, because earlier we were calculating everything at that moment only, but we are now storing the solution at a particular point, that is our last row. Means our last row, that is this one. That is why we have written this v of row minus 1. At this last row, whatsoever sum would be minimum, that we would be returning by this statement. So this is how we are doing for this particular TP approach. Here the time complexity, space complexity both are order of n square. Now comes the part for doing the solution with order of 1 extra space. Everything would be same the way earlier it was, right? But now the thing is we are doing in that vector itself. So here the thing would be that we will be, rather than using that extra space, we will be assigning everything to this input vector only. And again we will be checking, this was the thing we were using earlier also, but instead of that auxiliary vector, now we would be using input vector. Again same for this case also and same for this case also. And at the end, again we are returning from this input vector itself, but everything is same here, only that auxiliary vector is replaced by the input vector. So here the space complexity would be order of 1 and a time complexity would be again the n square only. So this was all for this particular question. I hope I was able to explain it in much better manner with all the approaches. Do let me know if you have still any doubt in the comment, and if you like the explanation, please do like, share and subscribe to the channel, and also do share with your friends. That would boost too. So this was all. Thank you.